Welcome to the UGC lecture series. This is the EPG Pathshala lecture series on computer science and we are talking about the paper data structures. In this particular module, we are going to talk about minimum spanning trees. This and the next module, we are going to discuss minimum spanning trees. In this particular module, we will be giving an introduction to minimum spanning trees and some approaches to solving the minimum spanning trees. That is what we are doing in this module. So, as you can see, we spoke about an introduction of graph, then we went into graph ADT and graph algorithms, operations where we talked about traversal. Now, we are looking at some applications of those traversals only. Here we are calling it as the minimum spanning tree. So, we will just look at the concept of minimum spanning tree in this particular module. So, these are the people responsible for the creation of this particular module and the learning objectives of this module is to understand the concept of spanning trees, to discuss minimum spanning trees and its properties and to explain the greedy approach to finding minimum spanning trees. In this module, we are not going to talk about any particular algorithm. All algorithms, most algorithms of minimum spanning trees use the greedy approach. So, we are just discussing what is the greedy approach to this and then we will go and explain the actual algorithms in the next module. So, the terms here are spanning trees, minimum spanning trees and the greedy approach. So, let us first discuss what is the meaning of a spanning tree. So, when a graph G is connected, you can do a depth first or breadth first search starting at any vertex and it will visit all the vertices of G. So, any spanning tree, a spanning tree is any tree that consists solely of the edges in G and at the same time includes all the vertices, that is called a spanning tree. So, just let us understand it again. What is traversal? When a graph G is connected, a depth first or a breadth first search will start at any vertex and visit all the vertices of in G. A spanning tree is any tree that consists solely of the edges of G and but includes all the vertices. So, if you take E of G, you have T tree edges and N non-tree edges. T is a set of edges used during the search and the N is a set of remaining edges. Now, let us take a complete graph here. It is just consisting of 4 nodes. So, a spanning tree of a graph is just a subgraph that contains all the vertices and is a tree. It need not be connected back, it should not be. A graph can have many spanning trees. For example, if you take that complete graph there, you will see that there are 16 spanning trees possible from that simple complete graph. The only condition we are saying here is that all the 4 vertices, there are only 4 vertices, all the 4 vertices should be part of the spanning tree and it should contain each vertex only one. So, what we are talking about is a tree and not a graph. So, what we are talking about, it is a subgraph that contains all the vertices and at the same time it is a tree. So, that is called a spanning tree. Okay. So, the first one and so on. Now, next we go to minimum spanning trees. So, the minimum spanning tree for a given graph, now first of all we can define a minimum spanning tree only if weights are associated with the edges, whether it is directed or undirected is immaterial, but weight should be associated with the edges. If that is so, you can define what is called a minimum spanning tree. What is this minimum spanning tree? The minimum spanning tree for a graph, given graph is the spanning tree which we have defined before with a minimum cost for that graph. So, if you take this complete graph, you will see that we have just done it, but if you will see it gives a minimum spanning tree with the minimum cost. How we arrived at this minimum cost we will see later, but this is the minimum spanning tree for this complete graph. Okay, it depends on the weight that is associated with the edges. Now, the spanning trees, either you can use a depth first search or you can use a breadth first search to create a spanning tree. When a depth first search is used, the resulting spanning tree is known as depth first spanning tree obviously, and when breadth first search is used, the resulting spanning tree is known as breadth first spanning tree. Adding a non-tree edge into any spanning tree is not possible because this will create a cycle. Okay. So, you cannot add that non-tree edge to any spanning tree. So, if you look at some of the examples we saw before, some of them had cycles. If you have a cycle, that means you have seen the vertex already, you should not go back to it. So, assume you have an undirected graph, spanning tree can be defined for directed, undirected, but remember minimum spanning tree can be defined only for weighted, whether it is undirected or directed. So, assume you have an undirected graph G is equal to V comma E, where V is a set of vertices and E is a set of edges. Spanning tree of the graph G is the tree t which takes v comma e of t, where e is the edges that result, that all tree edges are graph edges, but all graph edges are not tree edges. Tree and graph have the same set of nodes because all the nodes have to be included. All tree edges are not graph edges, which means all the graph edges are not counted or not considered for forming the spanning tree, and it is a tree, so that it has a root called R. The smallest set of edges needed to connect everything together, that is another definition for spanning tree. That is the smallest set of edges. From E you take a small set, but take the small set in such a way, there are two conditions: it should connect, all the vertices should be included, and at the same time no cycle should be formed. So, the smallest set of edges needed to connect everything together is called a spanning tree. Now, there are some properties of spanning tree. The first property is, suppose you have a graph G is equal to v comma e, and the spanning tree T is equal to v, that remains the same. E of t is a subset of the edges, and R a specified root of the tree. For any edge C in G but not in T, that is, it is there in the graph but not in the tree, there is a simple cycle containing only edge C and edges in the spanning tree. So, if there is an edge C in G that is not in T, then C will obviously not be there because it forms a cycle with the edges in the spanning tree. So, if you look at this example, if you add the edge, okay, if you add the edge IH, if you add the edge IH, a simple cycle will be formed IH GI. So, you should not add IH. Now, if you see here, the red lines will give you the spanning tree. A is the root, AF, FE, then AG, GI, GH, HD, AB and BC. So, all the vertices have been included, there are no cycles. Now, if you try to add an edge C, here we are taking the edge IH, then a simple matrix cycle will be formed IHGI. So, a simple cycle. Similarly, any edge you take HC, HC is another edge. If you try to add HC, you will have a simple cycle which will be formed HCBAGH. So, there is a small cycle formed. So, what we are trying to say is, the first property that we are trying to say is that if you have a spanning tree and a graph from which the spanning tree has got, if you take any edge that is not in the spanning tree and try to add it to the spanning tree, along with the edges of the spanning tree, what you get will be a cycle. So, that is what we are trying to say. That is the first property of a spanning tree. The second property of a spanning tree is, given the graph G containing the vertices and the edges, and the spanning tree T which contains all the vertices and a subset of edges and a root, for any edge in C in G not in T, there is a simple cycle which we have already seen. Moreover, inserting an edge C into T and deleting edge in Y gives another spanning tree T dash. So, what we are trying to say is, if you insert an edge and remove another edge, what you will get is another spanning tree. So, for example, suppose you have the edge HC, if you have the edge SC, then HC will form the cycle. We have seen this before. So, for any edge C in G, if you already have a spanning tree and you add an edge along with the edges of the spanning tree, it forms a cycle. That is what we first discussed. So, here we are adding the edge HC, you will form the simple cycle HC BAGH. Okay. Now, if you add HC, only thing you have to do is you delete another edge. So, AB. So, if you delete an edge AB, you do not have a cycle, but you have another spanning tree. Now, the subset of the edges that is used to form the spanning tree is different. So, now you have the subset of the edges as AF, FE, GI, GH, HD, AG, BC. Previously, you had AB, now AB is removed, and instead of that you have added HC. So, this is one of the ideas of a property 2 of the spanning tree. Now, let us see how you use building BFS and DFS spanning tree. So, use sequence structures before you can use, but put and get edges, not nodes. So, get edge SD from the structure. If D is not in the done set, add D to the done set, then SD is in the spanning tree. Add out edges DT to sequence structure if it is not done in the done set. So, for example, you have here example, you have the BFS queue. We are talking about the BFS traversal itself, we have the BFS queue. So, dummy and A, then you have AB, AG, AF. So, add that. Then you have next level you have AG, AF, okay, remaining as it is, but AB has been replaced by the neighbors of B. So, BG and BC, but A, you are coming from A, but BG G is already there and so on. So, this way you can do the depth first and the breadth first search. So, what you are doing is you are using a sequence structure and as before, but you are putting and getting edges, not nodes. Instead of edge node, you are getting an edge. So, get an edge SD from the structure. If D is not in the done set, it is already not done, then add it and continue. So, this is the breadth first spanning tree and this is the depth first scanning tree. Now, let us look at this. From A, remember it is a breadth first. From A, you will have AB, AG and AF. So, finished. Then you have to go from B. So, from B you have to go to the neighbors of B, but BG, that edge you should not count because G is already there. BC you will add. So, that is the only one. So, BG AB, AG, AF, then next is BC and from F you will add E. So, FE. So, you have BC and FE. So, that is the next. Next what you have is from G you have H and I and from H you have D. So, what you have done is it is a breadth first. So, A all its neighbors BGF, from B all its neighbors BC alone, then next is all the neighbors of A. So, you have to finish that level. So, B you finished, next you take G, from G you have I and H, the GI and GH in other words, and from F you have FE. So, that finishes that level, then you go to the next level. So, you have level 0, level 1 and level 2. Have you understood that again? Level 0 is A, level 1 is B, G, F, level 2 is all the nodes accessible from B, G and F. So, C, G, H, G, I, F, E. Then the last one is H, H, D. But the same graph, if you try to draw the spanning tree and you want the depth first spanning tree, then you start from A, go to G, then go to G's children, which is I, so that is 3. So, you will have 1, 2, 3. From 3 I's children E, 4. From 4 E's children F. Then after that you have A, G, I, E and F. Then from the previous last encountered F, you do not have any more children. Next is E, from E you go to D, which is on the top of the stack. Remember it is a stack data structures, that will help you to understand it. So, E you go to D. So, from D if you have not traversed, no, H, you go to H. From H you go to C. From C you go back to B. So, that is it. So, I will repeat again. The order in which it is traversed is like this and this is a spanning tree. Look at the spanning tree, it is not the same as what you had in BFS spanning tree. So, A to G. So, A is on top of the, let us understand it from the stack point. A is at the bottom of the stack, then you get G. From G neighbor, so I can go to B or I, it is going to I, so it goes to I. From I E, so 4, then from E to F, at that point I is over, A is over, so F has no more unvisited nodes. So, it goes to the previous node at the top of the tree, which is stack, which is E. So, it goes to D. Now, D is on top of the stack, goes to H, H is on top of the stack, go to C, C is on top of the stack, go to B. You could have had another spanning tree starting from, instead of going from G, you could have gone to B or F. So, that is possible, but still it is a depth first spanning tree. Now, let us go to weighted spanning tree. So, up to now we have just seen a spanning tree. We have not looked at which node to choose. We can randomly choose, normally we choose lexicography, not necessary. If A has 3 children and you want to travel, you go to A, B, C, you can choose one of them. Now, assume you have an undirected graph G, B, E with weights on each edge. So, it can be directed or undirected, here we are considering directed. The spanning tree of graph G is a tree T equal to V E T belonging to E. Tree has the same set of nodes, all tree edges are graph edges as before. Weight of the spanning tree is the sum of the, we have not said minimum. So, weight of the spanning tree is the sum of the tree edge weights. So, the minimal spanning tree, which is called as MST, very popular graph algorithm. Any spanning tree whose weight is the minimal, in general a graph can have many or several minimum spanning trees. Application of this is very large in today's scenario of transmission and all that. Applications include circuit board routing, networking, internet connections and so on and so forth. So, minimum spanning tree is a very, very important application of graph. So, let us define a minimum spanning tree more in detail. A minimum spanning tree connects all nodes in a given graph. So, an MST must be a connected and undirected graph, must be a connected and undirected graph. MST can have weighted edges. Multiple MSTs can exist within a given undirected graph. We will see about the others later. Multiple MSTs can be generated depending on which algorithm you are going to use. If you wish to have an MST, you can have an MST starting at a specific node also. It need not necessarily be, you can. However, if there are weighted edges and all weighted edges are unique, only one MST is possible. So, just let us relook at the properties. A minimum, first of all, a spanning tree has to connect all nodes in a given graph. So, that is the property of a spanning tree. A minimum spanning tree also has the same property. And then it has to be connected and undirected graph. Now, when you are saying minimum spanning tree, you have to talk about weighted edges. And multiple minimum spanning tree can exist for a given undirected graph. The number of multiple MSTs are generated depending upon the type of algorithm or the method of you are going to use to find it. You can have an MST generally, or you can have an MST starting at a specific node. And if the weighted edges are unique, that is each edge has a unique weight, then there is only one possible MST. So, in a weighted graph, you can sum the weights for all the edges in a spanning tree and attempt to find a spanning tree that minimizes the sum. We just said minimum spanning tree. So, there are several algorithms for finding a minimum spanning tree for a component. So, in a weighted graph, you have to sum the weights of all the edges in a spanning tree, all the edges, and you have to find a spanning tree with the minimizes this sum of weighted edges. So, there are several algorithms that can be used to find this, and repeated application to all the components in a graph yields a minimum spanning forest if you have many components. For example, to determine how an airline can service all cities while minimizing the total length of the routes it needs to support, typical application of minimum spanning tree. From that particular application, you can find out why minimum spanning tree is a very, very important data structure for an application of this sort. So, let us take an example here. This is an unweighted undirected graph. It is a tree formed by connecting, minimum spanning tree is a tree formed by connecting all the vertices with minimal cost. So, MST is tree because it is acyclic, you do not consider cycle. It is spanning because it covers every vertex, and it is minimum because it has minimum cost. So, the three properties minimum spanning trees, it is a tree because you do not allow a cycle, that is the definition of a spanning tree, not even MST, any spanning tree itself. It is spanning, it is called spanning because it spans all the vertices, you have to necessarily include all the vertices, and it is minimum because we are trying to find the one with the minimum cost. Okay. So, this is an example. So, let us see how this has been done. So, here it has started with a vertex, okay. So, and then from I think it has started from vertex V, and it has found 1 is the lowest. So, from that one it has chosen the one with the least from that second node vertex. So, that is there you have the 2, and then you go back, from there you choose the next 4, and then you have 6, 1 and so on. So, the total weight of this is the minimum. How to find out this we have not spoken, we are just showing you an example of a minimum spanning tree got from the previous tree. So, you will see the red edges are the one that has been used. So, from the first node you would select 1, go to the second node, select 2, go to the third node, then come back to the second node. Now, how does it come back, I will tell you that later. Then from there you take 4, from there you take 1, 6, go back, take 2, we will see. So, let us take the algorithm for finding this minimum spanning tree is interesting. There are many algorithms available. We will be taking 2 algorithms and discussing it in detail with simulation in the next module. So, now let us take a real time application of an MST. A cable TV company is laying a cable in a new neighborhood. So, if it is constrained to bury the cable only along certain paths, then there would be a graph represent which points are connected by these paths. Now, some of those paths might be more expensive because they are longer or require cable to be dug deeper, and these paths will be represented by edges with larger weight. So, a minimum spanning tree would be the network with the lowest total cost. So, what is our job? Our job is we want to lay the cable in a new neighborhood, and we cannot all paths are not possible. So, the path is determined by where we can lay the cable, and the laying of the cable there is a cost associated with it because of the length of the path or because of it has to be buried deeper, but we have to cover all the houses of the neighborhood. So, we want to find a minimum spanning tree with the lowest total cost. So, this is an application. So, we have a single source shortest path. Okay. So, that is one SSSP as it is called. So, you have a graph, and if you see there from A we have gone, or you can have a minimal spanning tree. So, what we mean by here is that from A only you are allowed to go. So, from A to B to C to D to H, I, F, A, G, that is a single source, and then expanded that to minimal spanning tree. Please note that a single source shortest path tree is not a minimum spanning tree, because the single shortest path tree is a fixed start node. MST at any point in construction we have a bunch of nodes that we have reached, and we look at the shortest distance from any of these nodes to a new node. So, what we are trying to say is, when I start from a point, I want to reach some points. For example, in the example there I have started from a node and I have selected 4 and 4 because I want to start only from that node. So, that is the single source. But in a MSP or a minimum shortest path, I will start from that first node, reach 4. Now, I do not have no constraint that I should start only from that node. So, I will select. Now, here I have 5, I have 8. So, that is the single shortest path, and this is the MST. So, the two are different, because we look at the shortest path from any one of those nodes to a new node, not necessarily from the starting node. That is why we have that. Okay. Now, we looked at two properties of the minimum spanning tree, if you remember. One was, if I add an edge, that edge along with the others will form a cycle. That was the first property. The second property was, if such a edge exists, then I can add that edge if I remove some other edge. So, that was, it still becomes a new spanning tree. That was what we were trying. Now, the third property is associated with weighted spanning tree. So, if I given a graph G and a spanning tree T, where E of T is a subset of E, for any edge C in G but not in T, there must be a simple cycle containing only edge C and edges in spanning tree, which have already been told. Weight of C must be greater than or equal to weight of any edge in this cycle, weight of that, because if that was not so, I would have chosen that edge instead. So, let us take an example. You have the edge G H, that is 5. Now, the cycle edges are, what are the cycle edges? G I, 2, I E 3, okay, E D 1, D H 1, H T 1, all have weights less than that cycle forming one, which is G H. So, if that G H was lesser, that would have been chosen. What we are trying to say is G I E D H G forms a cycle, because I have added G H. Now, that what we are trying to say here is that G H, the edge G H, will the weight of that will be greater than any of the edges that forms that cycle with that G H. So, that is what we are trying to say. In this case, G H has a higher weight 5 than any of the other edges G I, I E, E D and D H. So, the first minimal spanning tree algorithm was created by Otakar Baruboka in 1926. The algorithm is used to create efficient connections between the electricity work in the Czech Republic. Now, if you see that this is an algorithm, a graph algorithm, but it was not theoretical, it was created for the purpose of an application, but it is no longer used since Prim's and Kruskal's algorithms were discovered. These two algorithms will be going more in detail in the next module. But before we go to that, we will discuss the general approaches to determining a minimum spanning tree, and that is the greedy algorithms for minimum spanning tree. So, you extend a tree always by including the cheapest outgoing edge. So, at the cheapest edge that joins the disjoint components, delete the most expensive edge that does not disconnect the graph. If you have this basic idea, that is the greedy algorithm. So, you always have to extend a tree. The Prim's algorithm, that is the greedy algorithm 1, it extends the tree by including the cheapest outgoing edge. So, suppose you have 5 nodes in your box, that is 5 nodes have already been formed, then from any of these 5 nodes you try to find the cheapest edge. So, that is the greedy approach that is followed by PRIMS. Why is it called a greedy approach? We try to find an edge from the local viewpoint, that is why it is called a greedy algorithm. And the second algorithm, you add the, here the concept is different, you add the cheapest edge that joins the disjoint parts. There you add the cheapest edge from which is outgoing, here you add the cheapest edge that joins the disjoint parts. So, that is the two algorithms. This is the PRIMS algorithm. Both are greedy in the sense that cheapest is taken, cheapest outgoing edge is taken. Here the cheapest edge that joins disjoint components is taken. So, why does the greedy algorithm work? For simplicity, it assumes all edge costs are distinct. If you do that, let S be the subset of V, remember V is a set of vertices, and suppose E equal to U comma V, E is an edge between U and V, is the minimum cost of edge of E with U in S and V in V minus S, that is S is the subset, V is the whole set, V minus S is the other subset. So, between these two the minimum cost is UV, E is in every minimum spanning tree. So, that is why greedy algorithms will work. In this particular module, we have tried to understand the concept of spanning trees. We have discussed the minimum spanning trees and its properties, and we have explained the greedy approach to finding the minimum spanning trees. We have not actually gone into any algorithm as such, that we will be doing in the next module. We are going to try to discuss two algorithms, the famous two algorithms, the Kruskal's algorithm and the PRIMS algorithm. Both the algorithms are greedy approaches to solving the or determining the minimum spanning tree, which we will be discussing in the next module. Thank you.